In the preceding lecture, using the new concept of chemical potential, we examined the equilibrium between a binary liquid mixture, that is, a solution of a solute B in a solvent A, and the mixed vapor phase above the solution. We learned that for any multi-component, multi-phase system at equilibrium, the chemical potentials of the solvent must be the same in solution and in the vapor phase. The same relationship applies for the solute. We studied a very simple type of solutions called ideal solutions, where solvent and solutes obey Raoult's law over the whole composition range. We learned at the end of lecture 3.4 that ideal solutions are characterized by a 0 delta H of mixing, 0 delta U of mixing, and 0 delta V of mixing. We indicated that ideal solutions are very rare. Their rarity comes from the fact that for delta U of mixing to be 0 and delta V of mixing to be 0, solvent and solute molecules must be of very similar shape, size, and chemical structure. This is why benzene and methylbenzene can form ideal solutions. A wide variety of mixtures can be made with molecules differing in size, shape, and chemical composition. Actually, most solutions of interest are indeed very different from ideal solutions. Think about aqueous solutions of a protein or of a sugar, for instance. So, how much of what we've talked about for ideal solutions can we actually use for real solutions? This is the topic that we are going to take on today. We will initially discuss the behavior of non-ideal or real solutions, and then talk about two very important limiting behaviors, one for the solvent and one for the solute, as we consider very dilute solutions, and see that for such solutions, Raoult's law can still be very useful to describe the almost pure solvent. We will also see that under these conditions, the solute exhibits a very interesting behavior, which we call Henry's behavior. For conditions removed from the dilute solution condition, we will need to find a way to account for the departure from idealized behavior. This will be achieved by introducing the concept of activity and activity coefficient, which will still allow us to relate composition to chemical potential. In the second part of this lecture, we will change topic somewhat and start to discuss the concept of colligative properties. These are properties such as boiling point elevation, melting point depression, vapor pressure depression, and osmotic pressure. We will see what such properties have in common and how we can use them to determine the molar mass of a solute, for instance. In this lecture, we will treat colligative properties fairly qualitatively, using plots of the solvent chemical potential versus temperature, as we did in lecture 3.1 for pure substances. Our next lecture, lecture 3.6, will examine quantitatively probably the most important colligative properties of all, at least in the life sciences. Here I'm referring to the osmotic pressure. We start lecture 3.5 with a discussion of real solutions and examine the conditions under which Raoult's law behavior is still exhibited by real solutions. We then introduce Henry's law that describes the behavior of solutes in very dilute solutions, and learn to write the various forms of Henry's law on the basis of the specific units used for Henry's constant. For conditions where neither Raoult's law nor Henry's law can be used to represent the behavior of the solvent and the solute respectively, we introduce the concept of activity and activity coefficient. In the second part of this lecture, we will introduce the concept of colligative properties by examining a number of properties exhibited by dilute solutions of a solute B in an almost pure solvent A. Examples of colligative properties include vapor pressure lowering, boiling point elevation, and freezing point depression of the solvent, as well as the osmotic pressure associated with the solution. To close this lecture, we will use a graphical representation of chemical potential of a solvent as a function of temperature to show that mixing a solute with a solvent leads to an elevation of the boiling point and depression of the freezing point. In the preceding lecture, we concluded that ideal solutions have very specific properties. First, when solutions behave ideally, they exhibit no change in volume upon mixing. That is, the volume of the solution is equal to the sum of the volume of the pure components. Second, ideal solutions show a zero energy change upon mixing, indicating that the intermolecular interaction energies between like molecules are the same as between unlike molecules. These two observations imply that for a solution of two substances A and B to behave ideally, the chemical structure, shape, and size of A and B molecules need to be similar. This is why solutions of benzene and methylbenzene, two molecules differing only by a methyl group, behave ideally. The corollary is that most solutions of interest are not going to behave ideally. Hence, for most solutions, we should not expect Raoult's law to apply across the whole range of solution compositions. The example shown on this slide is concerned with the carbon disulfide propanone mixtures. A cursory examination of the partial and total vapor pressures versus composition diagram for this mixture suggests that neither the partial vapor pressure nor the total pressure vary linearly with the mole fraction of CS2. However, a more careful examination of the partial vapor pressure PA versus XAL diagrams indicates that Raoult's law is actually obeyed by component A when A is almost pure. The same observation is made on the other extreme of the composition range when B is almost pure, that is, when the mole fraction of A is close to 0.